This is a lecture on mechanics using the TB in frame and the idea of curvature and torsion of the curve. In this case, we'll let this parameterization R of t describe the path of an object. So the space curve is really the path of an object. So when I take the first derivative of R, I do indeed get the velocity. This is not necessarily a unit velocity, so I'm going to separate it out as magnitude and unit vector. This unit vector is the tangent to the curve. So the velocity equals the speed times the tangent to the curve. This is your linear velocity. And now we'll look at acceleration. So the next derivative is the acceleration, but I'm going to use this result here, that the velocity equals speed times the unit tangent and the product rule to find the acceleration. So by using the product rule, I have to take the derivative of the first term, which is right here, and that is the change in the speed of the vehicle, and that is in the tangential direction. Then I hold the speed constant and I take the next derivative of the tangent with respect to time. This is how the tangent vector, how the tangent to the curve is changing with time. If you remember from the second lecture, the one with arbitrary parameterization, we had this result. The change in the tangent vector with time, with respect to time, equals the speed times the curvature of the curve in the normal direction. So if you substitute that in, we get this important result from mechanics. It says that acceleration has two components. The first component is along the tangential direction, and it has to do with the change in the speed of the vehicle. The second component is in the normal direction, and there is no component in the binormal direction. This is a little bit surprising result. You would think there would be one, but there isn't. This also applies to force. If we neglect any change of mass with respect to time, we can write F equals ma and substitute that in. Then we have this normal component to the force and the tangential component to the force. Now for many cases, such as the one I'm going to do right now, the speed is constant. So this is 0, so the acceleration only has a normal component and the force is only also in the normal direction. And by normal, we mean the normal to the curve. Okay, if we're traveling along this curve, the normal here is pointing in this direction. The normal here is pointing in this direction. Here we're going to go back out in the other direction. These are the normals. Remember, the normal changes at every point along the curve, or it can change at every point along the curve. So using what we've done so far, we can derive these results for circular motion. Often this is done more in a trigonometric fashion, but we'll end up with the same results. So we start here describing the path, parameterizing the path of the vehicle around the circle, and that would be R. Big R is the radius of the circle times the cosine of omega t in the I direction plus, again, the radius of the circle times the sine of omega t in the j direction. So we have a circle, and its radius is R, and this object is going in that direction. So its first derivative is the velocity, and we're going to need the speed for later calculations, so we'll calculate that. Of course, it is the velocity vector, the dot product of the velocity vector with itself, and we end up with r squared omega squared multiplying sine squared omega t, and again r squared omega squared multiplying cosine squared omega t. Then we use the Pythagorean identity for trig functions, that the sine squared plus cosine squared equals 1, and that gives us the result that the magnitude of the velocity, that is the speed along the curve, is the radius times omega. Omega is the angular frequency. And that's a result, like I say, you can get from trig, linear velocity equals the radius times the angular frequency. We can also find the unit tangent. Remember, the unit tangent was the unit vector associated with the velocity. So we take the velocity divided by the speed, and that's our omega. We basically divide those the amplitude out from the sine wave. Sine stays though. So here is the tangent vector. It might seem fairly obvious to do this for a circle, but imagine that the object, the vehicle was traveling on a parabolic path or in some sort of a strange orbit. This is just the steps that you would go through, and of course you could duplicate them, hopefully now from other situations. To show you that this is the tangent, let's try to draw it. So here would be our circular path, say, and I'll put some I and J coordinate system on here. This is J and this is I. Okay, and now let's just look at this vector at different times. So when t equals 0, then this tangent would have a value of 0 in the I direction plus 1 in the j direction. So along the path, that's a vector like that. Makes sense, although poorly drawn, of course. When t is pi over 2, then this tangent would have, remember there's a negative sign here, it's going to be minus I. And as expected, it's like that. And then when t is pi, we shall have the unit tangent as 0 in the I direction, and this would be minus 1 in the j direction. So, and of course at 3 pi over 2 would be down here. So you can see that this does indeed give us the tangent vectors. I've just written here the acceleration, which was derived earlier for the general case, and included here the just the result for the case in which the velocity is not changing. Remember that the speed is not changing. Remember that the speed was r times omega, and we assumed that omega was constant and the radius of the circle was constant. And I might not have said it, but I assumed it and I should have said it. Okay, so here's our acceleration. So here I've just written the expression for the acceleration, which we derived earlier for the more general case, and we need only use this normal term because the speed is the radius of the circle, which is not changing, and omega was constant, even though I didn't say it, it was constant. So all we have is a normal component for the acceleration. Now we can find the unit normal and the curvature. So we take the unit tangent and get its derivative. By the results from the second lecture on TBNs, we have this. For arbitrary parameterization, the first derivative of the tangent vector equals the speed, the magnitude of the velocity, times the curvature, and that's in the direction of the normal. Of course, we know this is not a unit vector, so let me change colors here for a second. Okay, here are the scalars multiplying the vector, and if I write this derivative as a magnitude multiplying a unit vector, that unit vector is the normal, and we can use the magnitude to find kappa. So let's go ahead and work out the terms because we know we're talking about a circle. So the first derivative is here. minus omega times cosine omega t in the I direction, and then again minus omega times the sine of omega t in the j direction. We'll need the magnitude, and again we have omega squared times cosine squared plus omega squared times sine squared. Using the Pythagorean identity for trig functions, this magnitude is omega. So now we're just going to equate terms. The magnitude here is omega. Alright, I know that, okay, we're going to do it down here. So we've got the magnitude of the velocity times the curvature. We're trying to solve for curvature here. I know that the magnitude of the velocity is r omega, this the linear speed. Here's the curvature, and I know for this particular motion that the magnitude of the first derivative of the tangent is omega. So when I solve for the curvature kappa, I get the expected results. The curvature equals 1 over the radius. Remember, for the oscillating circle, the radius equals 1 over k, 1 over kappa, 1 over the curvature. So obviously the curvature equals 1 over the radius, and that is the expected result because since this is a circle line in the plane, the oscillating circle is identical to the circle itself. Now this is what we're working on. We know that the acceleration equaled the speed squared times the curvature in the direction of the normal. So here is the speed squared, r omega squared, the magnitude of the velocity squared. We now know that kappa, the curvature, is 1 over r, and from that we can write that the acceleration equals r omega squared in the normal direction. And that again is another result you can get from using trig, but we've derived it directly here just using the curve. Of course, the ones that you derive from trig are limited to a circle, whereas this is only an example. So you can follow this procedure for more complicated curves. So we can compute also the normal vector here. Here's a normal vector, and we get minus cosine omega t in the I direction minus sine omega t in the j direction. So let me show you that that indeed is a good result for the normal vector. So here's our circle again for the path of this object, and we'll look at, well, that's not such a good drawing. Okay, so we look at this expression at different times. That's what we're looking at. So let's let t equals 0. When t equals 0, n equals, well, cosine omega t will be 1, so that's minus I, and then sine is 0, so 0j. So that will give me a vector from here pointing in the negative I direction. Now let's move up where t is pi over 2. At pi over 2, the cosine is 0, but sine is 1, but because of that negative sign, it's minus j. So at this point, we have that vector. You can continue like that looking at pi, and you'll see you get two negative signs, so you'll have it pointing in the plus and the positive I direction, and down here it will be pointing in the positive j direction. So you see we have indeed found the expression, or this is a demonstration, example that we have found the expression for the normal vectors to the curve. So over here they're going to be at this angles. They're always going to be at right angles to the tangent vector of the curve. The force is mass times acceleration, and here's the expression for the force. And we're going to use that in the next calculation. Okay, here we're going to apply what we derived for the circle to looking at banked curves. So this is the angle associated with the banking of the curve of the road as a car goes into a curve. And the radius of the curvature of this curve, the radius of the curve, is r. I've been using capital R. We're not going to have any friction. And what we have here is we've got this force, which is pointing straight down to the center of the Earth, and the force due to gravity. And we can take the force that's exerted by the road onto the car here, right, that is F, and it has a component in this direction. Remember, you've got to use the complementary angle to theta. This would be the magnitude of the force, I want times the cosine of that angle. And then I have, we're going to derive this, we don't need it right now. And in this direction, we have the magnitude of the force times the sine of theta. Okay, so we just broke it up into components. And now we can equate terms. The magnitude of F times the cosine of theta equals, we're assuming that the car isn't flying off the track or losing traction, so that equals mass times acceleration due to gravity, the force due to gravity that's pulling down on the vehicle. This next term is a horizontal component, which should have been written in here, but it isn't, and that would be the magnitude of the force times the sine of the theta times sine theta equals the mass times the curvature times the magnitude of the velocity squared. And this is the result that we got from our analysis just of circular motion. So of course we can use this one to solve for the magnitude of force and substitute it into the other equation, and we end up, after we cancel the m's, with an expression for the banking of the curve, the maximum speed you can go around this curve without losing traction, and the radius of the curve. And depending on which ones you hold constant, you can solve for the other two. What I meant to say is you can solve for the other one. Here's the maximum velocity that you can take the curve at. It will be the radius of the curve times acceleration due to gravity times the tangent of the angle. Right. And we made use of the results that the curvature was 1 over the radius. You could also solve for the banking to try to figure out how you want to bank the curve if you knew some maximum speed that the vehicles were, legally going to come around the curve at, and you knew the radius of the curve, you knew the space where you had to make the curve. And you could solve this for the banking. So those are some applications of mechanics from using this kind of analysis. It's more general than what you usually, the way you usually look at circles, and because it's more general, it can apply to any different kind of space curve. Also, as you see how we've traced it out, you don't need arc length parameterization. You can use the arbitrary parameterization.